Welcome everyone. This afternoon's talk, HTTP 2 and you. Our speaker, Mark Nottingham.
Oh, so that is done. Okay. Hi. So my name is Mark Nottingham. Thank you for coming all the way down by the Oval to see this. I work for Akamai, and I'm also the chair of a working group in the IETF called HTTPbis, which, for better or worse, owns the HTTP standards. We've been working since about 2007 on a revision of the HTTP 1.1 specification, and we're just finishing that up literally right now. It's going to be RFCs in a month or two, hopefully. And we've also been working on HTTP 2.0 more recently, and that's what I'm going to talk about today. So basically, this is a talk that I've been going around and giving at conferences and at companies in different places to let people know about this work that we're doing so that it doesn't surprise them when a new version of the web's protocol comes along, and so to answer some of the questions. So I'm going to get through this talk hopefully fairly quickly so we can get to some Q&A at the end, because for me that's the fun part. So when I start talking about this, inevitably the first question people have is, why are we changing HTTP? Why are we changing the most widely used application layer protocol that's out there and the basis of the web? And it's something that's been stable for such a long period of time. And the answer is that there are a few different reasons, but it really comes down to the web, and the way we use the web has changed, especially in the last few years. And one of the ways that the web has changed is that it's a lot heavier and more interactive than it used to be. So this is a graph from the HTTP archive put together by Steve Souders, showing average page size in terms of download weight as well as number of requests. And I think this is a 2-year window you're seeing. This is actually probably about a year old now, so it's bigger than this. But you can see that the dotted line on the top, at the start, we had 79 requests to load a web page. And towards the end, in that 2-year window, it's over 100 requests just to load one web page. This is in the Alexa Top 1,000 websites. So it's an average of all of those. Transfer size start around 626K. Ends up at the end of that 2-year window, north of 1.1K, 1.1 meg, sorry, which is, that's a lot of data, no matter how you slice it. And so we have these heavier web pages, more interactive web pages that are putting more stress on the protocols. Furthermore, a lot of people have noticed in the last few years that web performance has a direct relationship to people's attention. If a website isn't performant, people will go somewhere else. Amazon has studied this, Bing has studied this, Google has studied this. This is a slide from Ilya Grigoryk's wonderful presentation, kind of a web performance primer that I'll give you a link to at the end of the talk. And it's showing that Bing did their study, and they were seeing that when you add delay to a page load, you lose queries per visitor, revenue per visitor, all sorts of different metrics go down. And so for a lot of people who make money off the web, this is a really important thing. Another thing that has changed, and this is another slide from Ilya's presentation, is that we're now using mobile a lot more. Mobile web has become the first choice for a lot of people around the world in terms of how they access the web. And unfortunately, because the technologies we're using to deliver mobile content, and 3G and now 4G, latency is really bad on mobile, and that intensifies all the performance problems we see in the web on mobile. So here, for example, they were doing some studies of Sprint 3G. Their average latency was 400 milliseconds. It's a bit better on 4G, it's 150 milliseconds, but those are Australia-style latency. Americans can't deal with that kind of latency. So, obviously something has to be done. And so as a result, if you kind of look at web engineering and how we put together websites today, you can see some really interesting techniques being used to work around or to mitigate the performance problems that people see. So for example, a very common technique right now is spriting. Rather than having a web page download 400 different icons, you'll put them all in one image, and you'll use CSS and maybe JavaScript, but usually just CSS, to create a window so that you can show which icon you're interested in a particular part of the page. That's Google and eBay. I forget who that was. Probably BBC, I think, actually. This one was eBay, and that one was Facebook. Thank you. Yeah. And it's a very common technique. It requires you to do a lot of things on the back end in your production pipeline that are kind of painful and convoluted. more importantly, it's creating, from an HTTP standpoint, now these aren't separate requests, they're individual, one big request, and if one of these icon changes, you have to invalidate the entire cache. You have to blow the whole thing away and start fresh from an HTTP caching standpoint, which isn't so great. You lose some of the flexibility and functionality of HTTP, and you're starting to create websites that are kind of like app downloads rather than this more dynamic protocol that we love so much on the web. Another technique is inlining. This is from the Apple homepage a little while back, where the web designer decided that we had some images we wanted to put on the page, and rather than making those separate requests, it was worth inlining them in the CSS. So you see here we've got a data URI in the CSS, and it goes on for a while. Come on. This is a short talk. There we go. It goes on for a while. And that's a really interesting decision because, this is base64 encoded. It's an inherently inefficient encoding. It has to be textual because we're in CSS. But they judged that it was worth blowing out the size of these resources over creating separate HTTP requests. Another technique you see from time to time, this is actually not quite so prevalent as it used to be, is sharding. The idea that, browsers have limitations in how many connections they'll use to a single host name. And so we'll use separate host names to blow out the number of connections we have available. This is from YouTube. That's Tim Minchin, who's really cool. And finally, another technique we see a lot is concatenation. We have all these different frameworks. I went out and kind of found a bunch of logos of them to create concatenated versions of your website. So you concatenate all your JavaScript, you concatenate all your CSS. Again, you're kind of making everything into these download once apps, which is a weird way to act on the web. And all of these, from my standpoint, are hacks, and I mean that in a complimentary fashion, which this crowd is probably more familiar with, which is they're an elegant way around a problem. You have a certain set of tools available to you, and you can find a way to say, well, if I use this tool in this really weird way that it wasn't designed for, I can get these effects. But because they're hacks, it also is evidence to me that there are intrinsic problems in HTTP that we can improve, that we don't have to, if we can get rid of these problems, we don't have to have these workarounds. The fact that there are hacks means that there are places in HTTP where performance is bad where you can't hack around them. So it's better to fix the protocol than to perpetuate the hacks. And throughout all of this, there's a theme, there's a mantra in the web performance world. Steve Souders, if you go to Velocity, he and everyone else there will say eliminate requests is one of the ways you improve web performance. You have to get the number of HTTP requests down. And that's interesting to me because, the underlying assumption there is HTTP requests are expensive. And so if you examine that, there's a couple of reasons. One is that HTTP 1 uses TCP really poorly. This is a visualization of a page load of, I think, New York Times a while back. By a tool that I wrote called htracer, which just sniffs the wire and shows you how HTTP uses the different connections. So here, the gray lines, which are a little bit dark, each one of those is a TCP connection. And the red dots on the top, so the requests, and the red lines in the bottoms are the responses. And these little tiny lines in here are the actual packets. It's a visualization of the packets. So you can see, you load the HTML, you get that down, the browser parses it, and then what does it do? It opens a whole bunch of TCP connections. You get your sins out here. Ow! You got your sins out here, and then you have these parallel downloads in a bunch of different TCP connections. And as you notice, we've got about 8 connections open to this one server, which happens to be an Akamai server. And the reason why we're using those 4 to 8 connections for most browsers these days on the web is that we have this phenomenon in HTTP called head-of-line blocking, whereby if I send out a request, the response to that request is implicitly associated with the request. There's not a request identifier or anything like that. You know as a client, okay, I sent that request, the next response I get will be the response to that request. And so there's an ordering problem there. If I use HTTP pipelining, which was introduced by HTTP 1.1, I can send out multiple requests, but the responses still have to be ordered. There's a whole mess of other problems with pipelining, meaning that it's really hard to deploy. But even then, I still have this head-of-line blocking problem. And so, from the client standpoint, that means that using multiple connections is the best way to deal with this. Remember that, the slide we had before, an average web page has more than 100 requests to load the page. And so this is a serious problem for browsers. And unfortunately, that's a problem for TCP because that makes these flows short and bursty. You know, you send a request, you get a response, you send a request, you get a response. You've got multiple connections open at the same time. You use them and then you throw them away. TCP was built and has been optimized over the years for long-lived flows. You only really get full utilization of the network when you have a long-lived flow in TCP. And so this is a problem for HTTP performance. TCP slow start is one of the issues that we run into here. So there are a lot of applications, and you see people creating things like download managers to download things from websites where they open a lot of different connections at one time to use as much of the network as you can. The problem is that's a very antisocial thing to do. TCP congestion control is actually a very good and useful thing because when you blast all those packets through your router or through your network infrastructure, if you get congestion, those congestion events cause severe performance problems, especially in mobile. You know, you start getting drop packets, you have to have some resends, and then you get a lot more latency involved than if you just, you know, go with one TCP connection. So congestion control is actually a good thing. There's a lot of modification of it being discussed right now. For instance, initial CWIN is now, you know, 10 by an experimental RFC. But
what are the X's of the graph?
Sorry?
What are the X's?
Ah, the axes. This is round trips, and this is segments. Sorry. That was a last-minute addition to the talk. Can you tell? So as a result, you know, HTTP is using multiple connections. This increases the chances of congestion events today. You know, you imagine you've got your mobile browser. It wants to load those 80 different assets. It opens up 8 different connections, blasts all those requests out, gets all the responses coming back. If it overloads your mobile network or any of the intervening network infrastructure, you have packet loss, you have retransmits. It gets really ugly really, really quickly. Buffer bloat is a factor in there as well, but I won't go into that. It's also resource intensive on the server side, of course, because you have multiple connections from every client. And to me, the biggest point is that this is really tricky for clients. If I'm a client and I need to load those 100 or 80 or however many it is assets for a web page, and I only have 4 to 8 connections to work with, I've got to figure out which requests do I put on which connection at what time, in what order, to get the best performance. That's what all the clients are competitive on. They want to be the fastest browser. And without more information, it's really hard to figure that out because any of those requests could be for a really big image or something with a lot of server-side wait time that makes it really slow. You know, it blocks the other requests in that connection. And so you have to be really careful about resource allocation. And at the end of the day, it's a guessing game for the browser. So it's very unpleasant. The other big problem that people have identified in HTTP performance these days is HTTP headers themselves are really verbose. If you look at any trace of a website load, you see a lot of repetition. So for example, this is a page load of etsy.com. First request on one connection. And all the requests I'm going to be showing you are from one connection, from a browser. First request, 525 bytes. You're getting the home page. You've got the user agent. You've got the accept header. Pretty standard stuff. Don't worry, that cookie's not my user credential. Second request on the same connection. There's something a little bit interesting here. 690 bytes, it's a little bit bigger because we've got a bigger URI and so forth. We have a referrer now. The cookies have changed some, but really there's only 226 new bytes in that second request on the same connection. Third request, we go and get some more JavaScript. And we've entered kind of a steady state. The cookies have settled down. It's another JavaScript request, so the accept header is the same. Your user agent doesn't change, of course. And the URI just changes a little bit. So again, about the same size on the wire, 683 bytes, but only 14 new bytes. Fourth request, and I'll stop now. It goes on, obviously. Again, almost 700 bytes, only 28 new bytes. And so we had 4 requests, almost 2,600 bytes in total. Of those, 1,797 are redundant. And the important thing is how many packets does it take to serialize this on the wire? So there's a guy, Patrick McManus from Mozilla, did a synthetic test where you take a web page, and he chose 83 out of the air, 83 different requests you have to make. if you assume an initial congestion window of 3, which is pretty common still with client implementations, and you assume that each request has about 1,400 bytes of headers, which is not uncommon at all with cookies and everything else that goes on the web today, it takes 7 to 8 round trips just to get those requests out onto the wire. So that's not getting responses to them. That's just literally, how do I chop these things up into packets and put them on the wire, taking into account TCP congestion control and slow start, because you have to wait a certain number of round trips before you can put more segments on the wire in TCP slow start and in congestion control. So 7 to 8 round trips just to get the web page loaded. If you think about that, it's kind of obvious why web pages are so slow, especially on mobile devices. You think about those latencies we're talking about on 3G and 4G, it's pretty obvious why it's slow. So, what are we going to do about it? Or what are we doing about it? SPDY was the starting point for HTTP 2.0. We went through a process when SPDY came about from Google, where we said, okay, it's pretty obvious there's demand pent up in the market for some revision and some performance improvements in HTTP. We put out a call for proposals for improvements to the protocol or replacements for the protocol. We had a few, and the working group selected SPDY as the starting point. And that was basically just to short circuit things and base it on running code rather than going off on some theoretical exercise and coming up with something from scratch. And you can go and use SPDY today. It's in Chrome, it's in Firefox, it's in a bunch of other places. If you go to Google with Chrome, you use it right now. And Mike Belshi and Roberto Pion, the guys who came up with SPDY, will be the first to tell you that none of the techniques we talk about here are new. You know, all of this stuff has been done before in various ways. Opera has their turbo mode where they have a optimized HTTP-like protocol that they use. HTTP-NG was an effort many years ago at the W3C to come up with the next generation of HTTP that fell on its face. And Waka was Roy Fielding's answer to HTTP 2.0. He just never wrote it down, unfortunately. And so none of the techniques are new. What is different is that we have the right people in the room, we think. We have a lot of implementers who are interested, and we have momentum in the market to get it done. And that's what makes it different than these efforts. This is a snippet from our charter, blah, blah. The big points are improving end-user perceived latency, getting rid of that head-of-line blocking that we talked about, improving how TCP is used, so forth and so on. Really, though, it comes down to the goal is it should be possible to use one TCP connection for a page load. It may not always be the case that it happens, but it should be possible that you should be able to use one TCP connection, get great performance, get the benefits of those longer-lived flows, make it less resource-intensive and more fair. TCP has this inbuilt concept of fairness where me loading a web page or downloading something shouldn't affect my wife talking on a VoIP call on the same internet connection. And so one of the things we're doing is separating the semantics of the protocol from the framing on the wire. So in HTTP 1, you have all these headers that are really payload. They're describing the application layer stuff. But you have a few headers that do something different. Like here, transfer, encoding, and connection talk about where does this message end and the next one begin, or content length, for example. They're used to frame the message on the wire, not really part of the semantic of the message. In HTTP 2, we're taking a different approach. It's a binary protocol, and we have these things called frames, and this is the frame header. You have a length of the payload, and a type, and a bunch of flags, and then a stream ID. And so the different frame types allow you to reconstruct the semantics of HTTP on the wire in a binary protocol. These are some of the frame types we defined. The really interesting ones are header and data. Settings allows you to kind of set up the connection and talk about how you want the connection to operate, whereas reset, stream, and go away allow you to kind of tear down parts of the connection or the whole connection in a controlled fashion. So, in HTTP 1, you have a request, and usually that's just a bunch of headers. Sometimes there's a body, but we'll ignore that for now. And then a response where you have the headers and then the data. And so in HTTP 2, you can serialize that on the wire for the request using one headers frame, and for the response using one headers frame and one-to-many data frames, or zero-to-many data frames, really. And the fun comes in because, remember, we have this stream identifier here on each of the frames. That allows you to tie the different header frames and the data frames together so that you know which request and response they belong to, but to intermingle them, to get you full multiplexing in both directions. So here, we have 3 requests in flight, all intermingled in both directions. And that allows you to have multiple requests in flight at the same time on the same connection without affecting each other. It also makes it a lot more, hopefully, secure, because in HTTP 1 you have the cross-site, what's the attack? Somebody help me here. Sorry? Request splitting, the request splitting stuff, yeah. Where you exploit the difference between how a proxy parses HTTP messages versus the server parsing HTTP messages, or the client, and you use that to inject new messages into cache. Because it's a binary protocol, it's a lot harder, really, to do that. Bye. Okay. So you get full multiplexing. That implies a couple of things. It implies you need a prioritization scheme. If I make all 100 requests from the client, from the browser at the same time up to the server needs to decide, okay, you've just made 100 requests. I've got this much bandwidth to you. Which one do you need first? Now, it can make some intelligent guesses about that. It can say, well, you probably need the CSS first, for example, or the JavaScript or whatever. But it helps for the client to give some hints as to, for example, what's in frame, what's in view in the viewport right now. So there's a prioritization scheme that allows the client to describe what's important to it and what the server should favor when it's sending stuff back down the pipe. Likewise, there's a flow control scheme. This is mostly for intermediaries. You have states where you need to be able to flow control how much data is flying through so you can control your buffer sizes. But the default advice in HTTP2 is if you don't need flow control, turn it off. Most endpoints shouldn't have to use it. They just have to respect their peers' flow control. The other big thing we're doing is header compression. If you think about how wasteful, or how much repetition was in HTTP headers that we saw before, the obvious thing to do is compress it. It's very tempting to say, well, why don't we just throw away HTTP headers and start new, because HTTP headers syntactically and semantically are a mess. You look at HTTP headers, especially headers like user agent, and who knows what's actually really in there. It's horrible. The problem is that we're chartered to, and I think for good reason, to be backwards compatible with existing web. If we go off and change what HTTP headers mean or introduce a whole new set of headers to replace the current ones, we have a transition problem. We can't do a flag day on the entire web. And so the practical solution then is to do header compression, to not touch the semantics of the headers, but to compress them as they go across the wire. So the first proposal in the earlier versions of SPDY was to use gzip. And Mike and Roberto did something really clever, which was they just used gzip, and they used one compression context in each direction, and they used the same compression context for every set of headers in that direction on the connection. So you imagine, okay, I've got a gzip context open, I'm about to send a request. Let's say the headers are, and it's just for the headers, by the way. So, you're about to send the headers, let's say they're, 2K for sake of argument. And you gzip them down to, say, 500 bytes. Fine. You send that request, you've saved some space, that's great. And then you want to send another request on the same connection. And because you're reusing that same gzip compression context, you've already primed all the dictionaries, it's all there. You send a second request, and because there's so much locality, that second request can get serialized in something like 10 bytes. It's fantastic. You're exploiting the self-similarity of the stream. Same for responses, too. And so, that's really cool because everybody knows how to deal with gzip. Everybody understands it. There's a bit of memory overhead which concerned people. You think about, I'm a proxy, all of a sudden now if I want a proxy connection, I have to hold 4 gzip contexts open for every connection I want to keep open. That's kind of not cool, but we talked about it. What killed gzip was this attack called crime. And this is basically, if you're inside of a TLS connection and you're doing compression, or any encryption, and you're doing compression inside of encryption, and the attacker has the ability to inject data, which this is the web, we've got JavaScript, we know how to do this, you can probe the space that's being compressed and recover plain text. So you could synthesize over potentially millions of requests. You could probe and say, okay, is ABC in there? Is ABC, ABD, so forth and so on. And observing whether or not, how efficient the compression is, you could recover parts of the plain text and then reassemble it. And there were demonstrations of this where they were recovering things like authentication tokens or cookies out of the headers. Because you're not compressing the entire body, you're just compressing the header, it actually makes it easier to attack. And that concerned the security guys enough where they abandoned gzip. So the newer approach is to come up basically with your own bespoke compression algorithm. That's what we've been doing. And we had a bit of a bake-off. The winner was what we are now calling HPAC, HTTP packing. It's a very uncreative name, which is basically coarse-grained delta coding. In other words, you send a request on the wire, and then for the next request, you say, okay, for that header, just use the same value I used last time, for example. And so it's the granularity of an entire header value. It's not over individual, potentially letters or small pairs of letters or whatever. And that coarse-grainedness makes it much harder to probe the space. And so the security folks, which I am not, but they've had a good look at it, and they're reasonably comfortable that this is resistant to attacks like crime. We did a bake-off. This is a visualization of header sizes for a page load. I think this was a page load of 4 navigations of Amazon.com. And so this is requests across the bottom and size of headers across the top. The blue line is HTTP1 native header sizes. So you can see they kind of spike up to 1,400 bytes, and then they kind of settle down into a steady state of 400 for a while, and then 600 for a while, and so forth. And the orange line is SPDY. That's the gzip approach. And you see they got really good compression across that. The green line is the HPAC approach that I just described. And you can see it's pretty darn close to the gzip approach, except for some places here where I think there was some cookie rotation and things like that. So we get decent compression or good enough compression, and that's really everyone's goal, is it just has to be good enough. It doesn't have to be perfect, without the security issues around it. The third thing that we're doing is very briefly called server push. And this is simply the idea that if I'm doing a web page load, a common pattern is you get the home page, get it back to the client parses the HTML, and pulls out a bunch of references and says, okay, well, I need the style sheets, and I need the JavaScript, and I need this and that. And so it makes those requests. But if you think about it for a few minutes, you realize that the server already has that information. It just sent the HTML. So why can't it just start sending proactively what it knows the client's about to request and save this round trip here, which for some people is a big deal. And so that's server push. It's just a mechanism that allows the server to push things into the client's cache. We describe it in terms of the HTTP caching model so that we don't completely break the rest of the protocol. You're pushing things into the client's cache that the client can then use. Now, the first and most common objection to this is that, well, what if the client already has it in their cache? If it does, you're wasting bytes on the wire. And the answer to that is basically, that's true, but we already have the ability to server push today in HTTP1, if you think about it. And that's, if you think back to the first part, inlining. We already have the ability as a web designer to say, okay, I'm going to inline this in the HTML of the page and force the client to download it every time it downloads the page. The other answer to that is, it's true, the client might already have it in cache, but there is another frame type back there that I kind of glossed over called reset stream. And that allows the client to say, okay, this stream number right here, I don't want it, reset it. And allows you to cancel a request without tearing down the entire TCP connection. And so if the client already has it in cache, it can say, no thanks, reset stream. And you've wasted a round trip's worth of a few frames of data, but you can cancel the download in one round trip. So where are we now? Google announced SPDY in late 2009. There was not a lot of activity for a while. I did one of the first non-Google implementations in Python, and that was a lot of fun. Just as an implementer, I've got to say, HTTP 1.1 is really complex to implement because there's so many different ways to parse a message. There are like 4 different ways to delimit a message in HTTP 1. You've got to get it exactly right. SPDY was a joy to implement because there's one way to do it, and it just felt right. And so that's what convinced me more than anything else. Mike came to IETF 80 in Paris and talked to us some about it in early 2011. And then in 2012, things started to pick up. Firefox shipped SPDY. We did our call for proposals that I mentioned, and we rechartered to start this work in kind of mid to late 2012, yeah. And the thing to note here is that down here, Netcraft in mid-2012 reported, I think that's May, reported 338 SPDY servers. So this thing is still just starting. It's getting a lot more adoption now, but we're getting close to done for HTTP 2. So I think we're at a good point with it. This is more recent. Right after we rechartered in 2012, we had a draft 00 come out, which was just a carbon copy of SPDY from Mike and Roberto that we used as the basis of the work. We had a meeting in Tokyo to start the work, then met again in San Francisco. And after San Francisco, we had a draft 04, which we designated as an implementation draft. And we said, implementers, please go and implement this. We're going to meet in a few weeks in Hamburg, and we're going to do an interop. And when we showed up in Hamburg, I was kind of expecting, I'd be really happy if we had, say, 3 implementations show up. We had 10, which was really cool. And we had good interop. We had Twitter interoping with Firefox and Akamai interoping with Chrome, and we were getting solid interop. So based on our discussions there in Hamburg, we released a draft 06, which was another implementation draft. We did interop for that in Seattle, hosted by Microsoft. And then towards the end of last year, we did a draft 09, which is our current implementation draft. And we're about to meet in Zurich in a couple of weeks to do maybe what could be our last development interop, where we're not, we're still nailing down the protocol for that. And I don't project out here because I've been very wary about writing down when we're going to finish. Everybody asks when you're going to be done. But talking to the implementers and everyone else, I'm pretty confident that middle of this year, we'll be done the technical work. We'll still have standards, hand-waving to do, and things to write down and so forth and so on. But the implementer's intention is to get this done and shipped very soon, because if this drags out too long and becomes too much of a theoretical exercise, we'll lose the attention of the browser vendors, and that's not good for anybody. So I'm hoping we'll have it shipping. We already have private builds, for example, in Firefox and Chrome. Hopefully they'll be public pretty soon. This is our current implementation list. So it's a Mozilla, it's in Chrome, it's at Akamai. There's a bunch of Node.js implementations. No Python yet. A lot of Python people here. And you can see we're starting to get the draft 09 implementations out. I think by the time in 2 weeks when we meet in Zurich, most of these should be draft 09. They usually leave it to the last minute. So how will it affect folks who use the web? First of all, the whole point of this is we need the web to be faster for folks. And so, the people who have the most experience with this right now are the folks at Google and a few others. These are some numbers that Google recently published where they're measuring the time from the first request byte to the onload event in the browser. For Google News, their median was down 43%. Google Maps down 24%. 95th percentile down 28% for Google Maps. Pretty solid numbers. Twitter published some numbers as well. This is a bit different because this isn't a browser experience. This is from their Twitter client, like on iPhone and Android. They do SPDY directly from the client and HTTP 2, and they're very excited about it because for the mobile case especially, it makes big wins. So you're seeing here, raw request latency. The blue line is HTTP 1. And the 99th percentile, 30 seconds, and it gets down to more like 20 seconds or 23 seconds with SPDY. For high latency connections, it's even better. This should be good for Australians. Yay. And this is probably a much more graphic way to see the difference between HTTP and SPDY. This is a page load. What was this a page load of? I forget. Wikipedia? Yeah, Wikipedia. And in HTTP, you can see these brown beigey kind of bits where the browser is blocked because it's waiting for connections to open up that it can use to service those requests. And so it kind of goes off this way. But with SPDY, because you can have full multiplexing, it can start them all there and finish them much more quickly. And so you're getting much better utilization of the network. People ask a lot, does this change my HTTP APIs? It shouldn't. If we change the semantics of HTTP, we're asking the entire web to change, and we can't really do that. So the semantics don't change. What will change is the leaked abstractions. The idea that TCP is supposed to be hidden by HTTP, but it has all these artifacts leaking up in terms of how HTTP uses TCP affects how you use HTTP, as described before. The spriting and the inlining, all that. So those will change. You won't need to do those things to get the most out of HTTP anymore. There may be some new bumps on your HTTP APIs to more fully take advantage of the protocol, but they're more like hints. It's not fundamental changes to the APIs. People need to rethink their connection handling. Because the connections will be longer lived, load balancing and failover and stuff like that will need to change. Both Firefox and Chrome are currently saying that they will require the use of TLS. Other browsers we don't know. And there'll certainly be other tools that don't require it, but it's going to be part of the mix. And people will have to get used to that.
What's TLS?
SSL, TLS? That thing, yeah. Sorry, that's IETF people have beaten SSL out of me. I can't say that anymore. Debugging, it's no longer a binary format, which makes me sad, because I love opening Telnet and typing something in. We do have some tools to mitigate that, and you can have a debate as to whether that's a good thing or not. But debugging is going to need to change. And it's going to take some effort. Oh, hello. It's going to take some effort to get the most out of the protocol. My hope, and I think everyone else in the working group, our hope is that the default implementations will be performant and give you much better performance than HTTP 1. But to get the absolute most out of the protocol, you have to make decisions about, like, for example, when do you push and what do you push? Tweaking things like flow control and prioritization. And so that's something that the community will have to build a body of knowledge about. And finally, if you're building APIs or doing non-browsing protocol stuff with HTTP, HTTP2 will change that as well. When you design an HTTP API today, you have to think about granularity a lot. If you make your APIs really fine-grained, that implies you're going to have to make a lot of requests to do certain things, and that incents you not to make it fine-grained. But with HTTP2, because the overhead of a request is much lower, you don't have to think that way anymore. And so things like batch operations aren't that attractive anymore. You just send all the requests and let the server sort it out. Headers as well, you can be a lot more descriptive in headers because you've got this compression mechanism at hand. I've got 5 minutes left, right? 2? Oh, come on. 3? All right, I'm going to stop there. I've got plenty more, but I think that's a good place to stop, and I'd queue any questions. Yes?
The compulsory TLS, how does it affect me if I'm a little guy hosting 20, 30 websites?
That's a great question. So, sorry. So the question is, how does the compulsory TLS affect people running 20 or 30 websites? That's a great question, and the answer isn't clear yet because we're still having this discussion. To me personally, it doesn't look like we're going to require TLS in the protocol, in the specification, but because the browsers are going, or at least some of the browsers are going to require it, it effectively means that to interoperate with those browsers, you'll need to implement, over TLS. And so the answer is either don't use HTTP2, stay on HTTP 1.1, or deploy TLS. Now, there are a bunch of people working on a bunch of different things to make it easier to deploy TLS for small and for large operators. That's a little out of scope for this talk, but that's not a static area. I think there's a broad understanding that the current administrative user, every experience of TLS pretty much sucks, and we need to do better, a lot better. Yes?
Did I understand you correctly that for every single session in the future we will have exactly one TCP connection, and that long-lived applications such as Google Mail are going to have the same TCP connection between client and server, and only one of them?
So the question is whether there will firmly be just one connection. No, that's, again, we haven't gotten to that point in our debate yet. The intention is that you should be able to use one connection if you want to. Clients will make their own decisions about when it's most appropriate to open a new connection. They'll be a lot more conservative, I think, about doing so. But because you don't have blocking on the connection, at least at the HTTP layer, it's more possible to do that. You can get TCP head-of-line blocking. And there's actually a whole nother effort. You know, once you do all this work in HTTP2 to make the protocol more efficient on the wire, you suddenly realize, oh crap, there's still a lot of inefficiency in TCP. And there's right now discussions in the IETF and elsewhere about TCP evolution or replacing TCP, if you follow the discussion of QUIC, Minion, SETP. And I expect in the next couple of years we're going to see, you know, the same kind of evolution happening in that world too. I don't know, somebody, up here.
What implications does HTTP2 have for optimizing the configuration of HTTP servers?
I'm sorry, could you repeat that?
What implications does HTTP2 have for optimizing the configuration of HTTP servers?
So what implications does it have for configuration of servers? It's not clear yet. It's certainly going to require a lot of tweaking and tuning. I think there will probably, you know, we have a whole cottage industry set up around web performance now, and best practices and so forth, and we'll need to develop that same body of knowledge for HTTP2. It's just early days right now. Yes?
Is there going to be a compatibility test suite or something like that to prove that it's HTTP compatible to compatible?
Sure. So the question is if there's going to be a test suite. That's a tricky area. Most standards bodies don't like to do test suites because that has a lot of legal implications, or at least, you know, official marks of compliance and so forth. We do have a group working on some tests. Everything, by the way, is on GitHub. So we have a repository where we're starting to collect tests. So it's http2.github.io. And if you look here, if I go to the spec repo, yeah, everything's here. We do have some tests. It's not clear how complete they're going to be. We'll see. Yeah. Are we? I think we're done.